We're going to use these ideas to resolve forces. Then looking at this question, this is how we draw it. And I know the 35 degrees is going to be there because we use this convention. The convention for angles is always drawn, or always measured rather, anti-clockwise from the positive x-axis. Positive x-axis. Are you used to that convention in drawing these things out? And I always use this convention, and it's a pretty standard convention. So if I measure an angle of 35 degrees, I would measure it from this positive x-axis, which is this axis here, and I'd go around clockwise. That's what the convention is telling me to do. So that's why I've measured it to there, guys. If I want to measure negative 35 degrees, what would I do? I'd go around clockwise. This would be negative 35 degrees to here. So if somebody had asked me to resolve two forces, 50 newtons at an angle of minus 35 degrees, that would have told me I've got to go around clockwise because the force would have been down there. If I want to represent a force in this direction, what would the angle be? It was the same force, but what would I say the angle would be? Sorry? 215, and how did you arrive at that? So, right, clockwise, so it'd be negative 215 or positive 180 minus 35, doesn't it? Which is 45, yeah. So I'd come round 145 degrees this way, and so I'd quote 145 degrees or minus 215. Okay? So that's the convention we use for measuring these angles. So I know that's where it's going to, what it's going to look like. Now I need to resolve it to its vertical and horizontal components. So what I'm after is, what's this effect of this force? I know you've been talking about this before, but I'm just sort of reinforcing it and checking we're all on the same hymn sheet here. I need to know what's the effect of this force in the horizontal direction, what's the effect of this force in the vertical direction, the vertical and horizontal components. Useful because if I'm working with forces, or any vector actually, anything that's got a magnitude and a direction associated with it, which is a vector, I'm often interested not in the overall size of this force, but what's the effect of this force in the vertical direction. Because it's lifting up, say, this weight of this building, what's the effect upwards? What's the effect of the structure? What's pushing it to the side this way? If there's more than one force, what's the overall force pushing it this way to the side? So therefore I'd have to work out what all the horizontal components are of all the forces and add them together to get the overall. Because the beauty of resolving into vertical and horizontal components is they're completely separate from each other. The vertical vector force has no effect in the horizontal direction. So if I'm only interested in the horizontal plane, I don't need to worry about any of the vertical forces and vice versa. So it's very common to find out what the vertical and horizontal components of the vector is. So to do that, I draw an arrow to the horizontal and an arrow to the vertical. And so I then have, effectively, this. So that's my 50 Newton force. This is 35 degrees. And this is the horizontal component. And this is the vertical component. So that's probably what you're familiar with seeing. And then what you're actually doing is shifting this force here, the vertical component, and putting it here. So I can make it into a right angle triangle. But don't forget, when you do that, actually the force is here, not here. Okay? So I end up with a right angle triangle. And So if I'd asked you to do this problem, which I'm going to do in a second, this is probably what you'd have drawn. So that's the 50 Newton, this is the horizontal, and this is the vertical. And that angle is 35 degrees. So that's the right angle triangle that I'm going to use using the laws of trigonometry to work out what FB and FH are. But not forgetting that it comes from this. Okay? Just using these conventions. Okay, so can you calculate what FB and FH are, please, using those big ratios that we were looking at? So if we do this, we get these values. So I'll have a go at this one now. Draw it out using the conventions and then tell me the values of the horizontal and vertical components of the force. This displacement vector that talks about here, displacement vector of 40 metres and angle of 120 degrees. So we've got 40 metres here, and we'll talk about these sort of angular motion soon. So this displacement vector of 40 metres, if this had been, starts off along this horizontal axis here, and then rotates, so this displacement vector of 40 metres is rotating round. And then after a certain amount of time, it freezes, and at that particular point, I'm 120 degrees, so I've come round 120 degrees now at this point. I might well be interested at that point at how far this component, so this might be some sort of shaft rotating, how far is this component displaced from the vertical, or from this zero here? What's its vertical displacement? Or what's its horizontal displacement? More normally, what's its vertical displacement? Because when we're talking about things like arms rotating, that produces a voltage. And so the size of the voltage is actually related to the displacement in the y-axis. And imagine this thing rotating around, starting here, then rotating round. If you imagine the y component increases, that is the vector here, and then goes left, and it is maximum value underneath, and so on. And as we'll see, that actually, if I've got just the y-axis, I end up with. So this is all to do with sine waves that we're going to be coming on angular motion. So finding the displacement in the y direction is something that we often call the displacement vector like this. If I'm going to draw this 40 metres displacement vector at an angle of 120 degrees, so I'm going to bring 120 degrees round here like this. So that's, I know now that's where the arrow is. So then I draw it on a right angle triangle. So that I'm actually not interested in 120 degrees, I'm interested in the fact that that's 60 from there round to 180. And then I calculate it. So I've got the FH, and what we were doing earlier is 40 times the sine of 60 degrees, which is 35, shall we say? The two significant figures. Now we know it's 35 metres, and I also know that FB, the vertical component, is 40 times the cosine of 60 degrees. We're not so often interested in the cosine, the horizontal, but we're certainly, as I've just been saying, interested in the vertical component. And that turns out to be 20 metres, the two significant figures. So, the only thing to do now is to say displacement 35 metres, 20 metres. What's to stop somebody at that point saying, okay, right, it's being displaced 35 metres up and 20 metres that way, so it must have reached here. That's the position. That's wrong, isn't it? It should be over there, right. So, in other words, finally we have to consider direction. And we use a convention again, but it's up to us. It depends on the situation. If these are structures on buildings, we might well be interested in most of our forces acting downwards, so I'm going to say the downward direction is positive. But I might easily be interested in situations where intuitively it's easier to expect the up. So you set your own convention, and it depends on the situation. I'm going to call up positive and down negative, and I'm also going to set a convention for left and right. And again, it's up to me. I could talk about right being positive and left being negative. So having set my convention and drawn my convention on the diagram, I don't need to draw this convention for the angle because it's set, but I do need to set this convention somewhere convenient up in the corner somewhere. And then finally I would say that my horizontal component is positive 35 meters, so I know that's up. Well, I've got that the wrong way around. Yeah, how about now? That should be the vertical and that should be horizontal. Then this will be positive and that will be negative. Okay? So in this question, we've got to decide how to draw it. Now, I'm interested in the magnitude of the resultant of these two forces and the direction of the resultant with respect to the 8 Newton force. That tells me that my datum line, if you like, my point of reference is going to be this 8 Newton force. So I set that to be in a convenient direction, and that's a convenient direction, because I now know I'm going to measure all angles anti-clockwise from there anyway. So I set my reference line as being the positive x-axis effectively. So this is my axis coming along here. So I'm setting an 8 Newton force positive to the right. Then I'm going to measure angles anti-clockwise from. So now I mark the other force, the 5 Newton force, inclined to an angle of 45 degrees to that. So in the drawing, in a situation like that, if I'm interested in the size of one force and its direction, or the resultant of that with respect to one of the others, that's the one. Okay. So finish drawing that out, and then what we've got to do is calculate the magnitude of the resultant of these two forces and the direction with respect to the 8 Newton force. So I've got two forces now. I need to find the vertical and horizontal components of each of these two forces and then add them together to get the resultant. Okay, so if I was drawing this, I'd set out my convention in the corner. So I now know right and up is positive, and then I draw it. So the effect is I've got to find out what the total vertical and horizontal components of these forces are. So I take the two in turn, I take the 8 Newton force and find the vertical and horizontal components, bearing in mind the convention, is it positive or negative using my convention. And then I take the 8 Newton force and the vertical and horizontal components and check the convention, the direction, and then add them together to get the total vertical and horizontal components. So if you'd like to do that, so I end up with the vertical component of the 8 Newton force is 0, horizontal is 8, and then I calculate the components for the 5 and they turn out to be the same because the angle is 45 degrees, both 3.5 newtons, both positive, so I add them together and I've got this. So now I've got to find the resultant. So draw it. I've got 3.5 newtons vertically in the positive direction and 11.5 that way. The resultant is going to be here. Now I can draw it to scale and literally measure the length of the line of the resultant, and you might well have looked at some ideas around that. You can either form the rectangle like this to find the length of it, or the top tail method where you put the 3.5 newton force on the end of the 11.5 and you end up with a triangle, don't you? There's one or two little ways, but we're going to do it by calculation. So now again I effectively shift this 3.5 newton force over here, so I end up with a right angle triangle. So this gives me my right angle triangle, which is what I'm after. So that's 11.5, this is 3.5, and I'm after the resultant. I'm after the size of the resultant, and I'm also after the angle, because I need to know the direction of this resultant. What am I going to use to find the resultant then? Right, so I use Pythagoras for this. And what am I going to use to find theta? Tangent. Yeah, because I know the opposite and the adjacent. Remember, r is the square root of 3.5 squared plus 11.5 squared, and we've also got that tangent of the angle is opposite over adjacent, so therefore theta is the inverse tan of opposite over adjacent, the angle whose tangent is opposite over adjacent. So again, these formulae are very important to remember when it comes to finding the resultant of two forces. So in this particular example, r is the square root of, oh well, we've done that. So what does r turn out to be? $12, rounded to two significant figures. So 12 newtons to two significant figures, and theta 17, the nearest degree. Sounds about right. So now try page 334, exercise 134.